This is a presentation on using threads in Java. It's based loosely on an old tutorial from java.sun.com that I can't find anymore. It's probably somewhere on the Oracle website. So, multi-threading. In Java, programs can have multiple threads. Java as a language was designed with multiple threads in, and you could use those threads very early on in the language. A thread is a separate computation process, but not necessarily a separate process in the operating system. Most often, a thread is a sub-process of the process that is the application. And I know that's way too many processes, but it'll all make sense here in a minute. Threads are often thought of as computations that run in parallel. They don't really execute in parallel. Usually, instead, the computer switches resources between the threads so that each thread gets a little bit of computing power and they just kind of take turns and eventually they all get their work done. Threads aren't the same as a core or a CPU. Your computer probably has multiple CPUs and the operating system allocates tasks to that, and mostly that is invisible to us as users. The idea of multiple cores or multiple CPUs is similar to threads, but usually that isn't programmer controllable. You can with some languages and some operating systems, but it isn't sort of standard to control that, whereas using threads is slightly more common. So a thread is a single sequential flow of control within a program. It's kind of one set of activities. The program is the process. The thread is within the program. Programs can be single-threaded. Most of the programs you write are single-threaded, and they have one thread of execution that happens. They can also be multi-threaded. Lots of programs that you use are multi-threaded. Web browsers are multi-threaded. They have a thread that reads, they have a thread that downloads images, they have threads that download sound, etc. So there will be lots of programs that you use on a daily basis that are multi-threaded. Visually, a single and multi-threaded program looks kind of like this. On the left-hand side, we have a box representing a program, and inside it is a series of arrows and little rectangles that represent a thread. So the thread's execution starts at the top and hits one of the little rectangles and does something, and then moves on and hits another little rectangle and does something. You can think of those rectangles as maybe loops or methods or something like that. And it carries on, and then when the thread is done, it just stops and control goes back to the program. You can have a multi-threaded program, which is on the right-hand side of this picture, in which case there's two threads represented inside the box, and each of them starts at the top of their respective box and executes some bit of code and moves on and executes some bit of code and moves on and executes some bit of code. And the difference is that both of those sequences are happening sort of in parallel. What really happens is one of them executes a little bit and then the other one executes a little bit and then the next one executes a little bit and then back to the second one. And the process, the program, and Java control which ones of those threads gets resources at which point in time. So why would you bother? Well, anytime you have a program that needs to remain responsive while it does something else, threads are a good solution. So most GUI programming is reliant on threads. Most servers are reliant on threads because they're things that need to keep doing stuff while something else is happening. A program that needs to wait for data from an internet source would be a good candidate for threading, for example, because you might send off a request for data and it might take 2 seconds, it might take 10 minutes, it might take overnight. You don't want your program to block and wait for that data to come. You'd like it to get that data and then do other things while it's waiting for the data to come back. There's some terminology that we need to keep in mind. Threads are sometimes called lightweight processes because it runs in the context of a full program, so it's not a full process. A thread gets its resources from the resources that are allocated to the program. So the resources allocated to the program are divided up by the threads. For example, threads have to have their own execution stack. So if you've got a program that has limited resources, it's not going to get more resources by multi-threading. It just shares the resources it has with its threads. There's a number of different concurrency models that are possible, and those describe the way that multi-threaded applications share resources. The original concurrency model in Java was a shared state concurrency model, which means that all the threads share resources and share the state of the program. Newer models are separate state or shared nothing, where there's very little shared between the threads and the results of the execution are shared as results, not so much as sort of shared resources. We're going to look at applications using this shared state model because it's still a little bit more common. You're likely to run into it. It's definitely more challenging to implement, and it's also the one I know the best. So for now, that's what I'm going to look at, but know that there are other models and you might want to educate yourself about them. So there's a couple of ways to use threads in Java. You can use existing classes, which is there's a timer class, for example. And you can write your own classes either by subclassing thread or implementing the runnable interface. And I'm going to show you examples of all of those. So for the rest of this presentation, I'm going to go through the presentation, but then I'm going to have separate demo videos and a place in the presentation where you should stop this presentation and go watch the demo and then come back to this presentation. It's just easier to do it that way than it is to try and shell out from PowerPoint into a presentation and make the recording all work. So we're going to start with a demo on using the timer class, and the timer class lives in java.util. The two classes that we're going to demo are timer and timer task. Timer task implements the runnable interface, and we're going to make another class that inherits from timer task. So you should stop right now and open demo 1. The code for it, if you've gotten the code from me, is in the subfolder called timer. So hopefully you've looked at the timer demo. There's a number of ways to stop that timer, and it's important when you are setting up threads that you have a way for them to exit. In general, threads should figure out how they're going to stop themselves. So you can stop the timer by invoking cancel on the timer. So you can do that from anywhere in the program. You can make the timer's thread a daemon by creating it with a true parameter, and then it stops running if all the tasks are done. And this is by far the most foolproof one. You can remove all the references to the timer object once all the scheduled tasks have finished, and then the thread will eventually terminate, or you can just exit the system. I showed you a couple of those in the demo, but stopping threads is one of these more tricky things about working with threads, and one of the things that's often forgotten and the cause of memory leaks. So it's important to keep it in mind. You can also build your own threaded applications in Java, and you can do that by subclassing thread or implementing runnable. In either case, you have to write a run method because that's the thing that is run in a thread. If your class has to already be a subclass of something else, then implement the interface, implement runnable, and I'll show you in a demo how you hand that off to a thread. If your class isn't a subclass of something else, sometimes it's nice to subclass the thread because you then get all of the thread behaviors, which gives you interrupts and waits and notifies and stopping and starting. And you're going to need a way to do that anyways, but you can have it built into your class. I don't think there's really a best in these choices. I think it depends on the context of the program you're implementing. At this point, we're going to stop and you're going to look at demo 2. I'm going to show you two demos. One is in the simple thread subfolder and one is in the simple runnable subfolder. One shows you what happens when you subclass thread, and the other one shows you when you implement the runnable interface. And if you've got the source code, you can kind of follow along. Remember that subclassing thread gives you access to the methods from thread, and I'll show you how some of those methods are used in this demo. So stop this now, go watch demo 2. So you've seen, by watching the second demo, the life cycle of a thread. And we kind of did all the things in the demo that a thread does. So we make a new thread and we call it start method, which puts it in the runnable state. And then the thread is running. And at some point, if there's multiple threads contending for resources, the thread will yield and let another thread run, and it's still in the runnable state when it's doing it. And so if it yields, threads can also become not runnable, in which case they're waiting for something. They're blocked on something, and they're not something that can be allocated running resources because they're not ready to run. They can return from the not runnable state back to runnable, and then when the thread is terminated, the thread is dead. So there's kind of the 4 states of a thread. The way you work with a thread is you create a thread using new. You have to call the start method to start the thread running. So you can't call run directly. You need to call start, and start will call the run method. Once the thread is runnable, it's scheduled for time with whatever is doing the scheduling. If the thread becomes not runnable, it goes into the pile of threads that are currently not runnable. Maybe it's waiting or sleeping or waiting for I/O. And as mentioned before, threads should arrange for their own death. Threads should die on its own and not have to be killed by an external process. So when a thread's work is done, it should just stop. If a thread becomes not runnable, it might happen because there's been sleep called on the thread. So sleep is a method. You can invoke it and you can say how long the thread should sleep. You might call the wait method where the thread is waiting for something to happen. If a thread is not runnable because it's waiting, then it has to be notified that it can now come out of the wait time. And there's a method that you can call on the thread that is notify or notify all. And it's kind of like a callback almost. A thread might be blocked on I/O, in which case the I/O has to complete so that the thread can go back into the runnable state. There is a stop method in Java threads, but it's deprecated. You're not really supposed to call it. So your run method in your thread should terminate on its own. It should be a way for the thread to know that it's done. You can get the state for threads. Sometimes that's useful. So there's a get state method that returns the state that the thread's in. It can be new, it can be runnable, it can be blocked, it can be waiting for a particular time, or it can be terminated. And sometimes when you're writing your algorithms, it's useful to be able to get those states. So a scheduler gives the illusion of concurrent processing. Java originally has a fixed priority scheduling. I'm actually not sure if it's still using fixed priority or if there's other ways to set up the scheduling for Java now. In a fixed priority scheduling, when a thread is created, it gets the same priority as the thread that created it. And you can set the priority with a call to set priority. The way that the scheduling works is Java chooses the thread with the highest priority and executes it. When that thread stops or yields or becomes not runnable for some reason, then the next highest priority thread gets time, and Java can preempt a thread for a higher priority thread that does need time. This strategy can be modified to avoid starvation, so don't assume that this is the strategy all the time. and base your algorithms on it, but it's the basic strategy. You can probably imagine how it would be easy to set two threads to a super high priority and the rest to a low priority, and then those lower priority threads would never get any execution resources. So it's important that the scheduler have a strategy that avoids starvation. If you've taken an operating systems class, you've probably actually studied algorithms to avoid thread starvation. Threads can be selfish, but shouldn't. So on the upper left, there's an example of a run method that just increments a number, and it just goes for a big long time and goes around and around in circles. So that's a bit selfish because this thread never has any space that it could yield execution. A more polite way to write a run method is if you have a run method that's going to take a long time, um, put a yield call to yield in it somewhere so that the thread has a marker for the scheduler that says, oh, I can give up the processor now for a little while if there's another thread with the same priority as I have. And then it makes it easier for the scheduler to slice the time up and all the threads get some resources. I keep saying time slicing, I haven't really defined that. The processor time is divided up into slices, which are then allocated to all the threads with the highest priority. So if there is 2 segments or 2 seconds of processor time and there were 3 threads that all had the same priority, it would just divide that up evenly. And the slices are very, very short. So a thread doesn't get a giant slice, it gets a little bit, and then another one gets a little bit, and then another one gets a little bit, and then the first one gets a little bit. And it kind of goes around in the round robin like that. So that's what time slicing is. We have the notion of synchronization. So there's asynchronous threads that contain all the data and methods for their execution. So an asynchronous thread can go off and it can run at its own pace, and it doesn't require sharing of any resources with any other threads. It's just doing its thing. And none of the other threads are reliant on what that thread is doing. And that's a beautiful model, except that it doesn't always work, because often we have threads because we're sharing data and state with other threads. So you might be writing to a file or reading from a file with threads. You might be writing, getting data from the internet and sharing it with some kind of processor. So often our programs have this producer-consumer model, and that requires synchronization of resources so that those threads can reliably and consistently share those resources and have behavior that is predictable. So we're going to do a producer-consumer example here in a minute. A producer-consumer is any program where data is produced by one thread and used by another, or produced by one process and used by another. If you're thinking in terms of web programming, a producer might go off and get some data where a consumer might use that data to do something else. In this producer-consumer example that we're going to look at, there are 3 main classes. There's the producer class, the consumer class, and the cubbyhole class, and I've actually called them that. The producer class is the one that produces data. In this case, the producer class generates an integer between 0 and 9 and stores it in the cubbyhole object. The cubbyhole object is just the storage device. The producer then sleeps for a random amount of time and then generates another number. So this is simulating something that goes off to the internet or some network sensors, gets some data, and then brings it back and puts it in a location. The consumer object reads the data that's in the cubbyhole, in this case the integers, and in a real world example would do something with this data. In my simulation here, the consumer does nothing but read it. It just reads the data and doesn't do anything else. So at this point, you should watch demo 3. If you are playing with the code on your own, it's in the cubbyhole folder, and we're going to, at this point, just look at the original code in the cubbyhole class. There's some commented out code that we will get to in the next demo, but for this one, we're just going to look at the original code. So stop now, go watch demo 3. So we looked a little bit at some of the problems in that demo and just a summary of them. In that demo of the producer consumer, neither class did anything to ensure that the consumer got every number and only got the number once, um, even though that would be ideal. So what if the producer is faster than the consumer? Or what happens if the consumer is faster than the producer? There's two aspects of synchronization that need to be thought about when you're writing threads. Two threads can't access the same object at the same time. So that's one aspect of the synchronization. And then we need to coordinate the operation. So when is there a number that's ready to be picked up, and when has it already been picked up, and when should we put in another number? And we're going to look at those two ways to coordinate threads. The first thing we need to do is we need to lock things. We need to make it so that the object can only be used by the thread that is appropriate, and only by one thread at a time, because we don't want them both trying to use it at the same time. In Java, you can do that by adding the word synchronized to a block or a method declaration, and that will let Java know that that block of code can only be accessed by one thread at a time. So the keyword is synchronized, and that automatically gets Java to use a system of locks on the objects and releases in the objects, and you don't have to do anything with semaphores and locks manually. You add the keyword synchronized, and all of that stuff happens for free. In the example I gave you, put and get were the critical sections in cubbyhole that need to be synchronized. So we can do that by rewriting the cubbyhole and just putting the keyword synchronized for the put and the get. And that means now that that cubbyhole can only be used by one thread at a time. So that's a really good start. Now when the producer calls the put method, Java locks the object for the producer, prevents the consumer from accessing it. As soon as the producer's call to put is finished, the lock is released, and Java supports reentrant locks. So A locks it and calls B, which also locks it, and it goes down that. So that's all supported again for free. So the sequence now looks something like this. We have a producer, and they put something in the cubbyhole, and then the consumer calls get, and it waits until the producer, so the producer is over here waiting until get's called, and then the consumer is waiting until put's called, and it all kind of works. That locking prevents the simultaneous access, but it doesn't help with the communication. The producer and the consumer still don't know when the lock is ready. So we can do that with a second Boolean that is called available. So there's a notification that says, is this thing ready? Available is true when there's an integer that hasn't been read. We can use the methods of thread that can tell us whether or not something is ready to be done. And so this is a call to wait, and then we're going to use notify all. We could use notify as well. So there's a set of three methods, wait, notify, and notify all, that let us manage this inter-thread communication in addition to having things synchronized. At this point, you should stop this again and watch the fourth and final demo. We're going to first uncomment the middle section of the code that's in the cubbyhole object and run the demo with that after commenting out the first section. And then finally, we'll comment out the last section, or comment out the middle section of code and run it with the last section of code uncommented. and you'll be able to see how wait and notify work as well. So stop it now, go watch the fourth demo, and then come back for the last couple of slides. There's two main concepts in terms of thread management, and that's starvation and deadlock. And it's the programmer's responsibility to make sure that your threads get access to resources to make progress on their tasks, which means you have to design your system so that starvation and deadlock don't happen. Starvation is when one or more threads are blocked from a resource and can't make progress. So if we add a second consumer to the producer-consumer example, we get starvation because the second consumer doesn't get enough resources and the whole system will hang. Deadlock occurs when there's two or more threads that are waiting on some kind of an unsatisfiable condition. So there's a wait that happens, and then A is waiting for B, but B is waiting for C, and C is waiting for A, and they're all waiting for each other, and nobody can resolve their wait. I don't have an example of deadlock in this little example. If you haven't already taken an operating systems class or some other class that talks about this kind of thing, read about the dining philosopher's problem because it's a great explanation of deadlock, and you can probably imagine how to apply it to threads. Deadlock's also known as a race condition. Deadlock only occurs when multiple threads need to have access to the same resource, and at least one of the threads needs to write to the resource. If you can design your program so that that never happens, you won't get deadlock. One way to do that is to make sure that shared objects are immutable. Then there won't be any race conditions because nobody's trying to modify the object. So in Java, strings and integers are immutable. So if you have a string and an integer and you're passing those between threads, then you're not waiting for write conditions because those strings and integers are not mutable. So this is an example from a tutorial. I did not write this example, and it's an example of a do-it-yourself immutable integer. So we have a class that's an immutable value. It has an int as a private member variable, and it has a constructor that takes an int and sets the value, and it can return that value as an int, which is great, but it can add something. It has an add method, and all it does is it returns a new immutable value by adding this value to that value. So this original object doesn't ever change. It's not updating its value because it's immutable. It's just sending a new value. And it will always have the value that it was constructed with. If you use an immutable integer in some kind of threaded calculator, perhaps, then we can have its current value as an immutable value, and it can call get value, which will return the current value. It can return set value, which gives it a new value and can set the current value to the new value. And it can add something, which calls the add method of the immutable class, returns a new immutable value, and sets it up. So now this kind of shared value that could be a contention because it needs to be updated is immutable, and you don't have problems with race conditions. Race conditions are complicated and a little bit confusing. If you have a threaded application and one of your threads is not ever getting resources, you probably have starvation. If you have a threaded application that is just not working at all, you probably have a race condition, and you have to really work out who's looking at which resources and what are they waiting on. Things I haven't talked about: it's slightly easier to manage threads using an executor. there's a good tutorial here on executors. It's super easy, but I didn't want to complicate the overall ideas. And there's a much more detailed tutorial on the topics found in this slide desk here at one of the Gencov tutorials. And if you enjoyed learning about this and want to learn more, I highly recommend working through that tutorial. And thanks for listening.